Ready? Okay, do I start? Can we cut this out in the beginning? Okay. Okay. Hi, everyone. My name is Jayden Gutierrez, and I am doing Chapter 3's Process Analysis Intro. Today with me, I have Gabriel, Arturo, I have Albert, and then I don't want to completely butcher her name, so I'm going to call her Anna. Okay, so moving on to the next slide. So what to expect in this chapter, we're going to start off with 3.1, how to draw a process flow diagram, which I will go over in a little bit more detail. Then we're going to move over to capacity for one-step process, how to compute flow rate, utilization, and cycle time, and then how to analyze a multi-step process and locate the bottleneck. And the last slide will be the time to produce a certain quantity and our conclusion. So for the first one, 3.1, how to draw a process flow diagram, you want to start off with understanding what process analysis really is. And it's the act of conducting a review and gaining an understanding of a business processes. The process analysis calls for reviewing kind of applications, technology, inputs, outputs, and the end results. The end result being the most important thing. Process analysis allows you to look through everything that's happening in your business, and then at the end discovers new ways on improving. My example was, how hard does an employee actually work and what can they do to improve? Wait times in restaurants, how can they improve those? Other things like that. So on to the next slide. So the best way to start the process of understanding process analysis is to build a process flow diagram. The structure at first glance looks kind of confusing, but when you really get into the details and every shape and box, you can kind of see what each one is. This structure is not just helpful in restaurants and salons. I think it's crucial to more vital operations such as hospitals. You know, are there enough doctors for each patient? Is there enough beds? Are medicines available for the patients? And that will actually help with the process analysis. For reference, we're going to talk about Subway. So in Subway, this is kind of like a detailed like recipe for a sandwich and including handling a customer. So we start off with the activity, which is greeting the customer and taking their order. The customer walks up, they ask for bread, they want it cut, you do the adding of the meat, cheese, onions, lettuce, whatever you want on the sandwich. And then the next person, if there is another employee, they are going to work on placing condiments, wrapping up in a bag. The other two employees work on offering a fresh value meal, offering the dessert, which could be a cookie, and then the last person could be ringing up the customer at the register. Next slide. So attributes that help with understanding the process flow. So just right off the bat, we're taking a look at the actual process flow diagram. So the triangle, the green one right there, that's the waiting customer. And then they're going to move to station 1, which is when they greet the first employee, and the employee asks, you know, what they want for the bread, what they want for the cheese, and other things like that. Station 2 could be going to the dessert. If the customer wants dessert, they can ask that one employee, and the last station would be paying, getting them all checked out. So one of the key words on the top is resources, which they like to use just to better understand the process flow. And the resource is the employee. That's what they're called. So the flow units is the actual graph below. The upstream is right there in the beginning with the green triangle. That is the beginning of the flow, and then the downstream is the end. And then just for reference, flow units, that's the journey from input to output. That's just a quicker way to think about it. And then just the last slide right here, we have key things to remember when utilizing this. So it's important to know what exactly process analysis is, but also when it should really be applied. And these are just issues on a regular day, or like increasing customer complaints. You know, if you go to a restaurant, if you go anywhere and you see a long line out the door, you're going to ask, you know, this business, are they really taking control? Do they have enough employees working today? What's the issue? So the carryout process is unclear. That's when you really want to start utilizing the process flow diagram. And then it's also, if you want to replace the old version and make new ones. If you just think that your business is going all right, but you know you can improve it, this is important to understand these smaller steps. The process analysis alone does not tell you anything about the flow rate, the actual numbers behind it, just enough useful information, and like a starting point to properly upgrade your business. So now we're going to move on to Gabriel.
Okay, so on to the next slide. So, all right, thank you, Jayden. All right, guys, my name's Gabriel. I'll be covering this section. So this is called capacity for a one-step process. So here's the first thing you need to know about a one-step process. So the capacity for a one-step process, it revolves around something called the processing time, which is how long it takes a particular resource to be processed. So for example, like the one that Jayden used was was like the sandwich shop. So at Subway, a person comes in, the employee greets them and will be like, hey, what can I get for you? And then they'd pick all their individual ingredients and whatnot, what kind of bread they want, all the way until the very end, which is where they would pay, and that would be the whole process. Anyway, so when working with process time, you want to think of it as an average time. You don't want to think of it as one particular time, because not all amounts of times are the same. One worker may be really fast at helping out a customer, and then another person who may be new or maybe not know so much about the business is likely to be a little bit slower and not as fast as the more experienced worker. All right, so on to the next slide. So this is part 2. So we're going to talk about what's called capacity. So capacity is the maximum number of flow units that can flow through a resource per time. So like, let's say, for example, a machine can create 50 pencils per hour. So that's how many things could be created by that individual machine in 1 hour. But of course, it doesn't just pertain to hours. It could be minutes, it could be hours, days, it could even be weeks or months. So how many of this can be created in a week? How many of this can be created in a month, and so forth. So the next part, it's really important that you remember this, just because I have a feeling we'll be using it. So you want to know the formula for the capacity. So the formula for capacity is capacity equals 1 divided by the processing time. So like I said, the processing time is how long it takes for something to be completed. So like the amount of time a Subway employee uses to make a sandwich, that's how long, that's gonna be the processing time. And then we're gonna talk about the maximum flow rate. So the maximum flow rate is it's a process that can be provided per unit of time. So this determines the maximum supply of the process. The process capacity is the smallest capacity of all resources in the process. So like, let's go back to the Subway example. How fast can an employee create a sandwich? So that would be, if they can create it really fast, that'd be the smallest amount of time that it can be made in. So on to the next slide. Okay, so this will be actually handed over to my classmate, Anna. She'll take over from here.
Hi, thank you, Gabriel. Hi, everyone. I'm Anasheh, and I'll be covering this slide. So on this slide, we're going to talk about how to compute flow rate, utilization, and cycle time. As you can see, it says like the demand rate, the number of flow units that customers want per unit of time. And how to compute flow rate. Its flow rate equals minimum demand, process, or capacity altogether. If demand exceeds supply and the flow rate is equal to the process's capacity, it's called the capacity concentrated. And we're going to go to the next bullet point. It's if the process capacity exceeds the demand, the flow rate will be equal to the demand rate, and that's called demand concentrate. Next point, utilization of process. The ratio between flow rate, how fast the process is operating, and the process capacity, how fast the process could be operating if there was any sufficient demands. To the next slide. Well, here we have the formula for utilization. It's utilization equals to flow rate divided to capacity equals to X on X equals 1. Cycle time measures the time between ringing up to consecutive customers, which is like cycle time equals 1 divided on flow rate. And the lead time is the time between an order being placed and the order being filled. And we're gonna move on to the video that is here.
Hello everyone, today we'll be going over the process analysis. So the primary care doctor has asked per day. Demand rate of flow per day. They're going to ask, what is the flow rate? What is the utilization of the doctor? What is the cycle time of a 10-hour workday? The first thing we're going to look for is the flow rate. So we know that the flow rate is the rate at which customers go through the process. So with the information we're given, we're only given the capacity and demand rate. The capacity is 60 patients per day. Demand rate, 12 per day. So with the information we're given, the minimum of here, what is the cycle time? So in a couple of workday, cycle time is time between the flow unit and it's the reciprocal flow rate. Meaning it's 1 over the flow rate. So the flow rate here is 12. So 1 over 12, right? But because we're assuming a 10-hour workday, we're actually going to 10, 12. That gets us 0.833 hours by. And this is how you find the flow rate.
So multi-step process and locating the bottleneck. The multi-step process relates to multiple tasks being carried out for one process. For example, this process relates to having like 3 employees serving a customer rather than having each employee serving a different customer. This help determines the flow rate of a process. Bottleneck is defined as being the weakest link, which is the resource with the lowest capacity within the process capacity. It doesn't matter if a resource comes first or last. What matters is the capacity of the resource when it comes to determining the bottleneck of the process capacity. For example, at an airport, the security will be considered the bottleneck as it slows down the process and interrupts the flow rate when boarding a plane. Continuing, we have a video right here explaining more on bottlenecking.
Forward, we're looking at a medium or long-term forecast horizon. We're going to then measure our current capacity and compare the two. We decide if and how the gaps fill. As part of that, as we're looking at our current capacity and any changes we might make to increase capacity, we need to recognize the bottleneck. So let's assume that you have a Subway franchise. And when it comes to making sandwiches at your Subway, you have to cut the meat, cut the vegetables, bake the bread, and then when the customer comes in, list them. So we want to determine the capacity for our franchise. How much can we actually produce? So as we look at capacity, we have to take into consideration what is the bottleneck most. So let's look at the amount we could produce in an hour. Notice that we can put 200 ounces of meat in an hour. And let's assume there are 4 ounces of meat per sandwich. So if we take those 200 ounces an hour, divided by the 4 ounces per sandwich, we find that in terms of meat cutting, we can make 50 subs per hour. Now, when it comes to cutting vegetables, we can cut 25 sandwiches with per hour. I don't have to do a calculation. When it comes to making bread, we can make 24 loaves in 4 hours, which means that in 1 hour, we can make 6 loaves. And let's assume that there's 1 loaf of bread, 1 sandwich. So we have 6 sandwiches an hour. Now we have the assembly. And let's assume that it's 5 minutes of assembly per customer. So if there are 60 minutes in an hour, divide that by 5 minutes per customer, then we can service 12 customers in an hour. Let's assume each customer is just ordering 1 sandwich. So as we look at the capacity, how many sandwiches we can produce an hour, we need to look at the bottleneck production process. So meat cutting produces 50 sandwiches worth, vegetables produce 25 sandwiches worth, bread produces 6 sandwiches worth, and the assembly 12 sandwiches worth in a single hour. So we can see that making the bread is the obvious bottleneck. And so it is going to limit our capacity. We can't make more than 6 sandwiches an hour because of the time it takes to make bread. Then we have to ask ourselves, if the forecasted demand is more than our current capacity, how could we bridge the gap? Well, let's suppose there are changes to our company that would increase bread making 30%. We could increase assembly by 20%. We could increase meat cutting by 15%. So let's look at that. If we increase bread making by 30%, so that take that and multiply it times 1.3, then we can now make 7.8 sandwiches an hour. With the meat, we could cut 50 sandwiches worth per hour. With our new method, we could increase that 15%, multiply that times 1.15, and that would mean we could make 57.5 sandwiches an hour. For assembly, use our new assembly method, it would increase by 20%, multiply that 12 per hour times 1.2, and we're now able to assemble over 14 sandwiches per hour. But notice that the meat cutting, any improvement in the meat cutting makes no difference in your capacity. Any improvement in the assembly time makes no difference to your capacity because of the bottleneck. So when you're looking at dealing with the gap or comes to demand and capacity, where do you look is the bottleneck? If you're not improving, increasing the amount of production, bottleneck is not to capacity.
So in the video, the speaker describes how making the bread is the longest process when making a sandwich. Therefore, it's the bottleneck of the process.
The bottleneck. Our production process. That is activity. The you need to
So continuing, non-bottleneck resources have a slack capacity and have utilization levels that are less than 100%, whereas bottleneck resources has a utilization of 100%. Generally, a resource would have a utilization of less than 100% for the following reason. A non-bottleneck resource has extra capacity relative to bottleneck resources. In the scenario of a demand-constrained process, even the bottleneck resource would not be at 100% utilization. To define bottleneck even further, we can compare it to CPU and GPU terms in bottlenecking. GPU and CPU are both computer parts that determines the speed of the data being transferred within the unit. Bottleneck occurs within this process when there is a limit on how much data is being sent for processing or how much data that can be processed at the same time. If there is a huge difference in processing speed between the CPU and GPU, then bottlenecking will occur. This occurs when the CPU isn't fast enough to process and transfer data. This is a result of having a processor that cannot keep up with the data being transferred. In this picture, you can see that the CPU is being bottlenecked as the data is not traveling fast enough to the GPU.
Okay, so my name is Arturo Garza. I'm going over the 3.5 section of the chapter, the time to produce a certain quantity. And so basically, we're going to start with the one employee. Let's say given we have one employee, let's say their processing time is 120 seconds and the capacity is half a customer per minute. And then the cycle time for the single employee case would be 120 seconds per customer. And so let's say we're trying to figure out the time to produce 20 sandwiches. So Q will always represent time to make the units that we want. And so we're going to see right here, the time for 20 units is 120 seconds per customer times 20 customers, and that gives us 2,400 seconds. So that's going to be our Q, which is, again, the time to make the units that we want. And then this equation right here is just a simpler way to say it. It's the time to make units equals the cycle time just times the Q, which the Q was the 20 right here. So it's pretty straightforward equation. And then we also go over what if we had 3 different employees available. And so as seen as previously in the book, with 3 employees, our bottleneck was the one employee that was 46 seconds long. And so that's always the one we're going to use with the equation. And so the time to make 20 units equals the cycle time times the 20 customers. So in this case, the cycle time would be the 46 seconds, our bottleneck, times 20 customers, and that equals 920 seconds. However, this isn't an exact equation, and we're going to see why right now, because we still have to account for the lost time through the process, which I'm going to explain now. So systems work under either worker paced or machine paced manners. So the worker pace is each worker is free to work at their own pace, And when they are finished, they move it to the next resource. And the machine pace is all the steps are connected through like a conveyor belt, and all steps work at the same rate regardless of capacity. So the worker pace could be comparable to the sandwich or Subway um, analogy that we've shown multiple times. So basically, say someone starts doing the bread, putting on the spread, and then they go on to the next worker. The next worker adds, let's say, the meats and the cheese. They go on to the next worker, does the veggies, stuff like that. And so the thing is, the worker that's supposed to be putting in the veggies cannot actually start doing their part until the other two people are done. And so we have to account for that time lost during that first run through where the last employee and also the second employee, they're not doing anything during that time. So we still have to account for that. And then I just went over the example of the worker pace. Subway, or like honestly any fast food works for this example. Like say I used to work at a fast food place where you would have to wait for the kitchen to cook certain foods, and then that food be given to someone that was bagging the food, and then the person bagging the food then passed it on to someone who would hand it to the guest. And so in that way, it's the same way where I can't, or like say if I'm bagging the food, I can't do anything till the food's ready, and then the person handing out the food can't do anything until it's all packaged. And then a machine paste, it's pretty self-explanatory. It's like if you've seen any conveyor belt, like making any like cars or most electronics run like this as well. Like the conveyor belt really like never stops. It just keeps going. It might take like a second to like add on something, and then it keeps going on. Everything's pretty uniform. Everything's the same. And then nothing's like really waiting during the conveyor belt. Everything, all the times are the same, and the flow is consistent. And then so basically we have to figure out the time through the empty system, which is, like I said, the time it takes the first unit to flow through the empty process, which is the process with no inventory. And then the reason there is no inventory in this case is because say worker number one just cuts the bread and adds the spread. Worker number one can have 3, 4, 5 sandwiches ready before number two is done adding all the meats and the cheese, because that might take longer. So there's an inventory stacked up there, but during the first run through, there's no inventory. So that is what this is referring to. And so the time through an empty machine pace process is the number of stations times the cycle time. And then for a empty worker pace process, it is the sum of all the processing times. And so our sum for our worker pace process, the one the example we were using, is 120 seconds. So every order following would be the 120 seconds plus the 46 seconds we said before that it takes to finish the whole process. So we have to make sure to add the 120 seconds it takes for the first process. And so obviously after each customer comes in, you're gonna add like another 46. So if we have 20 customers, the first person waits the basic amount of time, but then you have to add 46 on top of every customer. So by the end of it, you would have the equation right here. So it'd be, you'd have to multiply by each person that goes through to give you the correct time. And then we'll have a video showing right now.
Okay, so I'll go ahead and play the video at the end. Let me go ahead and share my screen. Okay, so here's a video that you guys can see. It'll help. My bad. That was an accident. Let me play the video. Okay, so that concludes that video. So if you guys want to go ahead and do a conclusion. So basically in this video, we covered things like the process flow diagram, which just explains the process of how things work throughout the video, how things work throughout a business. And then we also talked about flow rate, so the rate at which things are produced or the rate at which things are put out, at which they're completed. We also talked about bottleneck and the cycle time, and the types of systems. So like it sounds, the types of systems. Okay, that's it. This was fun. Yay. I'm gonna go ahead and stop screen sharing.